Alrighty. Well, I know I said in the last video, at least I think I said in the last video, that we were going to do 2 videos of 2 example problems, but I think we can just fit both of them in one video. The first one will be a little bit easier, and the second one will be a little spicier. So this first one, well, let's just talk about what the problem is. We have 2 functions here, f of x being 2 over 3 plus x, and g of x is 3x plus 4 divided by 2x minus 3. And we want to just find their inverses. Okay, so we're going to find their inverses, and then we'll confirm graphically that we have indeed found the correct inverse. Okay, so we're going to start off with f of x. So let's just put that over here for now. Oops. Okay, so think about what we did before. All we need to do is just change x and y algebraically. So, sorry, I kind of froze there. So again, this is just y equals 3 plus x. Sorry. All right, I'm ready. This really just says y equals 2 over 3 plus x. And so to create the inverse, to invert it, we'll say, because I guess invert is a verb, we're really saying x is equal to 2 over 3 plus y. Okie dokie. Well, if we're going to do that, well, there's actually 2 ways you can think about this. I think the way that seems obvious at first is to multiply both sides by 3 plus y. That's probably how, that seems the more obvious way to me. So on the left side here, we will have x times 3 plus y. And I'm not multiplying this out intentionally, equals 2. Okay, now I need to get rid of the x. So remember, my goal is to find eventually y equals stuff on its own. Okay, well, I'll divide now by x. So divide by x, divide by x. We'll get 3 plus y is equal to 2 over x. And now we just got to subtract 3. And we get y equals 2 over x minus 3. And so that is our inverse function. So that would be f inverse of x would equal 2 over x, minus 3. Again, we should just take note here. Remember that f, when I have this little -1 there, it looks like an exponent. It's not an exponent. So remember that this is not, let's just move this over. Is not 1 over f of x. That's not what that is. If I wanted to say this, I would write it like so. Make it super clear. You take f inverse of x and raise that to the take f of x and in parentheses raise that to the -1 power. That's how I would imply that. All right, but let's take a look at the graphs of these 2 functions here to just confirm that. Let's take a look at the graphs just to make sure that we indeed found the right functions, or function rather. Okie dokie, so here we are in Desmos, and I've graphed our 2 equations. So the red one is the original function, the blue one here is the inverse. And we can see here that if let's actually plot in here, y equals x as well. So y equals x is right here. We can see that if I was to fold this red graph over this purple line, that this little bump over here, I think we can see that this little bump will land on top of the blue one here. And same thing with this red one will land on top of this blue one. Right? We can also just check a couple points here. So for example, on the red graph, we notice here actually the red graph doesn't look like it has an x-intercept at all. But you can see that this point right here, the y-intercept on the red graph, the original function, is 2/3, and that corresponds to the x-intercept on the blue graph, which is also 2/3. So that's a way that we can kind of check that. Alrighty, let's go back to our spicier example now and see if we can create that inverse. Okay, so we're back, and I also, before we even get to creating it algebraically, I want to talk about how what I mentioned in the last video where writing out the steps and then doing them backwards, like we were able to do on this one, doesn't quite work in this case. Because, okay, again, step 0 is to input your x value. Input x. Oops, not 0. Input x. Stand by. Sorry about that. Okay, step 0 is to input x, as usual. Okay, what is step 1? This is kind of awkward because there's like 2 step 1s, right? Because on top, you multiply it by 3, but on the bottom, you multiply it by 2. And so, you might be able to work this one out. I don't think it kind of works out exactly the same. Like, I don't think the reverse of this is to then divide the top by 3 and then divide the bottom by 2. I don't think this works out. If you can figure out a way to actually do this out, verbally, I would be very impressed and very curious to hear about it. But I personally have not quite figured it out yet. So this is an example of where we definitely, it'll make our lives easier to just do it algebraically. So to invert this thing, again, we're going to just switch x and y to start. So before it said y equals this fraction. So now it's going to say x equals 3y plus 4 over 2y minus 3. Okay, this one's a little odd. Now, we could do a number of things to this, but I'm going to actually do this just like what we did in the last one over here. So I'm going to multiply both sides by 2y minus 3. 2y minus 3. What happens? Well, on the left side now, we will get x times 2y minus 3 equal to 3y plus 4. Okay, this one is going to be a little bit messy because remember, we do need to get all the y's in one place all together because again, we want to get y equals something. Okay, so I think what we're actually going to want to do here, well, let's get all the y's to the same side. So let's just put everything on the left side just for now, just see what happens. So I'll put x times 2y minus 3 minus 3y minus 4 equals 0. The minus 4 didn't really need to join us, but why not? Okay, well, this y is trapped inside the parentheses, so to join it up with the other y, it has to come out. So I have to distribute that x, unfortunately. Why does that happen? Sorry. Okay, sorry about that. I don't know why that happened, and it kind of messed me up. But as I said, we're going to have to distribute this x. So we're going to have 2xy minus 3x minus 3y equals 4. And I ended up just putting the 4 back on the other side, as you can see. While we're here, we can move the 3x over. So we're going to have 2xy minus 3y equals 4 plus 3x. Now, this one's not going to be pretty, but it is still doable. You can see here that I could get a y by itself by factoring it out now of that left side. So you can see I'll have y is equal to, y times 2x minus 3. It's equal to 4 plus 3x. And now all I have to do is divide both sides by 2x minus 3. And I'll end up with our inverse, which is 3x plus 4. I'm just going to reorder that there. Divide by 2x minus 3. And you can see here, this should make a little bit of sense because we can see that in the original function, excuse me, sorry, I kind of confused myself there, but this one's very, very interesting because check this out. What we just found was, again, the inverse function. So this is g inverse of x. It looks awful familiar. And hey, what the heck? This is actually the exact same function as we started with. And so this is possible because this is just a function where it turns out that its input, it is its own inverse. And so what would that look like in terms of a graph? Well, remember that the graph of some function and its inverse, they're just reflections of each other across the line y equals x. And so what must be the case then is that this graph, to start with, is already symmetric across the line y equals x. So the function would look something like this. Again, here's the line y equals x right here. This graph would have to have some kind of shape that looks, I don't know, maybe something like this. And what, that's really messy. And there's a number of ways you could draw this. We could have a shape that looks like this. And so this function, well, this point already gets mirrored over here. And so when you draw its inverse, it would just look exactly the same. So let's actually look at what this specific graph looks like in Desmos. Oopsies. Here we are. This red graph here represents the function that we were starting with, and therefore also its inverse, apparently. And we can see here that this graph looks pretty dang symmetric. And I try to make sure that our scale is 1:1 here, so we can see, well, any point that exists already on it. So this point right here, let's find, well, we could look here at their x and y intercepts. The x-intercept right here is at -1, -1 1/3, comma 0. And the corresponding point, which would be, again, by switching the x and y coordinates, is 0, -1 1/3. And so this graph is already symmetric across the x and y, the line y equals x, and therefore is its own inverse. We can just double check a line over here. Hey, this point right here, when x equals 5, when y equals 5, we can see where it crosses. Right here is at 2.714. And the line x equals 5, which would happen right here, is at 5, 2.714. And so indeed, this point, if anywhere on this point, anywhere on this graph, you have some point xy, the corresponding reverse coordinates of that point are also on the graph down here of a function that is its own inverse, which definitely can happen. Alrighty, so hopefully that was very interesting and helpful, and we'll catch you in the next video, in which case we will finally put together the idea of inverses and how you can get the inverse of an exponential function, which is kind of the whole purpose of this.